I'll be presenting today on semantic caching. A little bit about me. I have a job at Oracle Cloud where I'm a lead engineer on a project called OCI Cache, where we offer a managed Redis and Valkey as a service. I personally have used Redis and Valkey for many years. And as part of my contribution to the Valkey project, I maintain a special SDK that allows you to build modules or extensions to Valkey using the Rust programming language. And with these modules, you can add all kinds of interesting features, such as creating custom data structures. We'll be touching on a module called valkey-search later in presentation, which is built actually in C++, but there are also options to build modules in Rust. Personally, I'm a fan of Rust. Let's first summarize a basic caching or regular caching. Why do we use it? Well, sometimes we need to decrease the load on our databases because some of the SQL queries we run can be quite slow. Or we may be hitting a third-party API to retrieve information, and that can cost real money, in addition to increasing the latency of our application. So what we do is we take the input, we generate some kind of a unique user ID based on that input. Usually we'll run a hash function, and then we'll check our cache for the presence of key with that ID. And if we found, we just use the corresponding value. However, if we don't find it, that's when we actually do the slow computation. We run the database query. Then we take the results, we store them in Valkey, and we specify a TTL. And one of the advantages of Valkey as a caching technology is it gives us ability to create varying TTLs for different keys. So that gives us flexibility in our business logic, because some data can be cached for a few minutes and some can be cached for a few hours. And if we can cache data for longer, that can be very valuable. However, we need to keep in mind that the longer we cache the data, the less accurate it becomes. For example, if we query third-party API providing us weather information, that weather will be fine for the next few minutes or maybe even an hour. But if we cache that information for several days, it's going to obviously be not very accurate anymore. And the way we store data in Valkey is just key value pairs. So here we have key1 with corresponding cache value and its TTL, and a different key with a different value and probably a different TTL. Let's talk about now semantic caching. But before we dive into semantic caching, we're going to cover certain basic concepts, and it's going to involve a bit of math. And I assure you it is important because depending on how you implement your semantic caching, how you leverage vector similarity search, you can get very different results. You can either save money and scale your applications, or you can actually waste money by storing unnecessary information. So with regular caching, we look for exact match, right? But with vector similarity search or semantic search, we're looking for similar items or semantically similar. So how do we do that? We don't compare strings. We compare numbers or embeddings or vectors, and we accept a certain similarity threshold. And what are vectors? Well, vectors, they're numbers with magnitude or size and direction. Here's an example of vectors in two-dimensional space. On the left, we have two vectors pointing in largely the same direction. We can see that the angle is close to 0. Here we have two vectors that are orthogonal to each other. So the angle is close to 90 degrees. And here we have two vectors pointing in opposite direction. So their angle is close to 180 degrees. And we can just visualize and see how these vectors are more similar than these vectors. Well, in reality, we don't have two dimensions. We're going to have hundreds or thousands of dimensions. And our vectors will look like this, a whole bunch of numbers. And to compare them, we have several approaches to choose from. One approach is something called cosine similarity, where we don't compare the magnitude or size of vectors, just the angle. So here you can see that the angle is close to 0, and cosine is adjacent of a hypotenuse. So in this case, of an angle that's close to 0, the cosine of 0 is going to be close to 1. So these vectors are similar. In case of orthogonal vectors, where the angle is close to 90 degrees, the cosine will be close to 0. So it's obviously less similar. And here we have a 180-degree angle, and the cosine will be close to -1 for opposite vectors. Another approach is to actually do the actual Euclidean distance. More math. So the x squared plus y squared equals z squared. You can see the formula right here. And then to calculate the distance, we actually do the square root. Now, one way we can save the computing cycles is that we don't actually have to do the square root, which is an expensive computation. We just leave it as a square, and then we compare things. So the smaller this distance is, the closer the vectors are to each other. And another approach is something called inner product. So the way it works is we multiply the components and sum the results. So here is an example of vectors A, B, and C. And when we compare A, B, we get 11. And when we compare A, C, we get minus 17. So we can easily tell that A and B are much more similar than A and C. And basically, it measures how two vectors point in the same direction. There's something else that we want to cover, and that is called normalized or unit vector. So here's let's say we have a vector 3 by 4, and we can calculate its magnitude to be 5. 3 squared plus 4 squared, square root of 25 is 5. What normalized vectors do is they shrink or expand the magnitude to 1. So here, what we do is we simply divide its dimensions by 5. So 3 by 5 is 0.6, which is this distance, and 4 divided by 5 is 0.8, which is this distance. So this blue vector is the normalized version of this larger red vector. And the interesting thing that with the normalized vectors, their inner product is the same as their cosine similarity. Because at the end of the day, inner product is angle similarity times vector length, and when vector length is 1, it is the same. So here's another example. If we have vector 1, 0, so it's just one direction, goes like this. And then we have another vector 0.7, 0.7, and you can visualize it to be just like a 45-degree angle. Well, here's the math. Inner product is going to be 0.707, and cosine of 45 degrees is also 0.707. Let's summarize. So with cosine similarity, we compare angles. With inner product, we compare directional alignment. And with L2, we compare the actual distance. But now that we've covered how to compare two vectors, how do we compare, let's say, hundreds, thousands, or even millions of vectors? We can use brute force approach, but for obvious reasons, that's going to be slow. So this is where an algorithm called hierarchical navigable small world comes in. And what it allows you to do is to find the approximate nearest neighbors. And it's essentially a log n time complexity versus O(n) complexity for brute force. And that's what we need to use when we compare millions of vectors, and each one has thousands of dimensions. Because the more vectors and the more dimensions, the longer it's going to take with brute force. The way to think of HNSW is kind of like cake with layers, or let's say city with highways, roads, and side streets. So the top layer is going to have just like fewest vectors and the sparse connections. And it is the highways. It's going to get you where you need to go fast. However, you will then need to go to the middle layers, where you'll have more and more connections and more vectors. And they're like major roads. They help you get closer to where you need to go. And a bottom layer will contain all vectors. It's going to take up the most memory. And it's like local streets. It's get you precisely where you need to go. But this is going to use the most memory. Depending on the number of vectors, you will also have a different number of layers. So if you have just a few thousand vectors, you'll probably have less than 5 layers. But if you have 100 million or so vectors, you can have up to 12 layers. So it'll take more memory, and obviously the search will take a little bit longer. So the way it works is that your search algorithm would choose a random node or vector in the top layer. It'll compare it to your query input, and then it will search all of the neighbors for that vector and find the best match. And then it'll go to the bottom layer, to the corresponding node, and repeat the process. Here's the visualization. We start here. We find this match. We then go to this next layer. We search near our vector, and we find this match. We go to the next layer, and we repeat the process until layer 0. We'll find the best possible match. So the benefits of HNSW are speed and accuracy. However, the downside is memory. All these layers will take up more and more memory. And the biggest usage of memory will be the number of dimensions. So for example, when I prepared for this presentation, I first used a local model called TinyLlama, which gives me 2,000 dimensions. And it wasn't very accurate. I switched then to another model which gave me 4,000 dimensions, and I could see the difference in search results. So each dimension is a float 32, which is 4 bytes. So if you have 4,000 dimensions, that is 16 kilobytes just for that vector. In addition to that, you will have some connections in a graph. So if typically you have 16 neighbors for each node, so that's, let's say, 8 bytes for each pointer. And then there's some overhead for the graph overall. But you can easily see how the most memory is taken up by the vectors and by the number of dimensions in the vector. There are some alternatives. As I said, you can just use brute force. It's going to be slow. And for very large data sets with billions or hundreds of millions of vectors, there's an approach called inverted file index or product quantization. Let's try to put it all together. Let's say we have a user input called "What is machine learning?" And here we have valkey with vector similarity search, valkey-search module. So what first we're going to do is we're going to take this input and we're going to call an LLM. That call will allow us to generate the embedding. And those calls are fast and cheap. So what is machine learning gets converted to this vector. And then we're using valkey-search to search the vectors stored in valkey. And we can find a match because we have here a record with ML definition and the similarity threshold is 0.94. And here you can see that on our query, we specified similarity threshold of 0.90. So that gives us a match. We then can use this vector and a corresponding cache to return the information to the client application. It's going to be fast and very cost efficient. However, what if we don't have this record? We don't find a match. Well, then we're going to have to query LLM, pay for it, wait, and then we will cache the response for the next search. However, what if we were to lower a similarity threshold? And the way to think of similarity threshold is just like TTL. The longer TTL is, the less reliable data is going to be, and the lower the similarity threshold, the less reliable your semantic match will be. So if we didn't have this ML definition, and if we were to lower similarity threshold to, let's say, 0.75, we would then match on deep learning because its vector is 0.76, similar to our input vector. And then we could use a corresponding cache for deep learning. However, if we didn't have deep learning, and we were to lower similarity threshold to even more, to 0.50, then we would find Python basics. And we can easily see how Python basics is just not that similar compared to the what is machine learning input. Okay, to summarize it all, we generate a vector for the input. We then run vector similarity search to find a match in vector database, which in our case is valkey. If match is found, we can check for a cache also stored in valkey. And it's a good question when we want to store vectors and then separately store caches and then expire one and keep the others. To be honest, a vector without a corresponding cache is not that useful, so you might want to choose to expire them both at the same time. But you can choose to keep them for different duration. So if vector match is found, we use the corresponding cache. If it's not found, then we query LLM and we cache the response. However, if vector match is not found in this scenario, then we're going to store the vector in the database, query LLM, and cache the response. When it comes to storing data in valkey, we have several approaches. We can either store our vectors and a cache in separate keys. So here we have a key with the prefix doc, which actually stores the vector. And when we build our valkey-search index, we will tell it to only index fields that begin with prefix doc. And then inside those fields, only index fields like vector. And this will allow it to ignore these cache keys. And then in cache keys, we just store them as simple key value pair strings, and we specify TTL. So this way, we can retain the vectors and expire a cache after a period of time. And then we'll have different keys for key 2. So we'll have doc key 2 and cache key 2. Okay. Another option is we can use valkey hash maps and store everything in the same key. So here we'll have key 1. We'll have a vector stored here. That's going to be the 16 kilobytes of data. Then we'll have another key where we'll store the cache. And if we're using valkey 9, we can actually specify TTL just on this because valkey-9 supports a feature called hash field exploration. If we're not using valkey-9, we can then store the exploration time separately as just another attribute or key value pair. And then in our client application, we can choose whether it's okay to use it or not. And we can store additional attributes, for example, input. The actual user input is not needed for caching system, but it can be useful for debugging purposes. And then we'll have another key with its own vector, its own cache, and so on. So why does this matter? It matters because we want to scale applications and save money on LLMs. In fact, it can be just not even about money. The question is, are there enough GPUs out there? How fast is it going to be? Because if we have one agent calling another agent, which in turn can call a third agent, and each of those agents has its own LLM, that's going to get much, much slower. And it's also similar to a microservice architecture, where you have a microservice that calls another microservice, which may call a third microservice. And each of those microservices will need to query a database or do some expensive calculations. So if we can cache things at the first microservice or maybe second microservice layer and prevent this series of cascading agent or microservice calls, that can be a very powerful technique for scaling our system. So the pros and cons is, as I mentioned, savings. And in a way, we can think of it as that we can trading our expensive GPU LLM hardware for just commodity hardware necessary to run cache. And we will either need to run these GPUs ourselves and then run our own LLMs on top of it, or we can be using some service providers such as OpenAI, but they in turn also need to run GPUs. And also with caching, we can improve latency. But the biggest downside, of course, is the accuracy of our search results. Because with regular caching, we kind of have one dimension of TTL. But with semantic caching, we also have the second dimension of accuracy or semantic similarity. So if you lower those thresholds low, your application will just store and serve information that's just not very relevant. Now, we talked about these two types of calls to LLMs. And again, the very first one is what we do to generate the embedding. And those are very cheap. However, what's really expensive and slow are the actual GPT inference calls, where it costs orders of magnitude more, and because they have to use bigger models to run your inference. We don't want to use semantic caching in usual situations. For example, if the data is changing very rapidly, so then by simply storing it, it may already change by the time it's requested again, or if it's not requested again for a very long period of time, and by then it already changed. And those are similar to how regular caching might not be the right solution. But in case of semantic caching, we also need to take into account that if we need very high accuracy and we have a very sparse data set, and again, we will lower similarity threshold low enough that the matches will just not be relevant. So keep those concepts in mind when deciding how to implement semantic caching. Okay, now let's talk about valkey-search. So what valkey-search allows you to do, again, it's a module, it's an extension to Redis. So it allows you to turn valkey into a vector database, take data that's stored in valkey in either JSON or hash maps, and create indexes on top of it, and then run vector similarity searches. And use valkey as a cache. So it's a dual purpose technology. If we were not using it, we would have to have like a different database for just vector searches. And there are technologies out there for that. And then another solution to use as a cache. And here we're combining it. And because data is stored in memory inside valkey process, those vector similarity searches will be very fast. Now, the biggest downside, of course, is that it's can require a lot of memory. And also, you'll need to be able to get the valkey-search module onto the server. At the end of the day, it's just a library. So you either have to control your infrastructure to be able to upload this module there, or a cloud vendor that you're using has to support it. And most cloud vendors today support valkey-search module with the recent versions of valkey. So what valkey-search does behind the scenes, it'll create this HNSW index using command ft.create. And one caveat is that whatever your LLM returns, the number of dimensions in index has to match that. You will then load data either as JSON data structures or as hash maps. And valkey-search will automatically index specific fields based on how you created the index. And then you'll be able to write commands such as ft-search. Now, the reason commands begin with ft is because originally when Redisson module was developed on Redis codebase, it was targeting full text search use case. So that's the origin of the names, FT for full text. And when valkey-search came along, it needed to match that API. Okay, let's do a quick demo. So I built here a dashboard to allow me to do semantic caching. And I'm going to type a question, let's say capital of France. What it's going to do behind the scenes is it's going to query a local LLM that I'm running. And you can see that it returned me a result. Now, I also have this dashboard where I can look behind the scenes, and it tells me what is actually stored in Valkey. So you can see here that I'm storing in two different keys, doc prefix and cache prefix. And this is just a unique ID. I'm actually using a hash function to generate it. And then I'm storing input text for debugging purposes. And I'm storing the 16 kilobytes of embedding. That's the vector. And then I'm also storing the cache response with a TTL. So I'm choosing to retain my vectors, but expire my cache. Okay, and that is what's returned in my query. Okay, well, what if a different person comes along and says, instead of capital of France, France capital? And in traditional caching, that would result in a different hash ID, and that would require another call to an API LLM. But here you can see the response came back very quickly. That is because it was able to do vector similarity search, match it to this vector, to this vector, and then use a corresponding cache response for at least for the next 200 plus seconds. Well, let's try something else. What if somebody say German capital and search that? Well, that is not correct. Capital of Germany is not Paris. So why is this happening? Well, it goes back to that similarity threshold. You can see here they specified extremely relaxed, 0.1. If I were instead change it to, let's say, 0.9, you can see how it's now thinking, and then it gave us the correct result. And behind the scenes, we can see that it's now storing vectors for both texts, and then it has the corresponding cached content for both user queries. So the question was, why do we use different similarity thresholds? And the question is, you have to make a trade-off. How much do you want to pay for LLM? Because if you increase this threshold and you never get similar prompts, you will be just paying to query LLM, and then you also be paying to cache this data, but you will never find a match to your query. So again, in reality, you will probably never want to go down to as low, to 0.1, but you can play with maybe 0.9, 0.8, depending on how accurate you need to be. So as I said, just like TTL, right? Time to live. If you cache data right now, the weather right now is going to get less and less accurate with time. So same thing here. The lower the similarity threshold, the less likely you're going to have a good match. Let's look at the code that actually powers this application. So it's built using this framework called Micronaut. And you can see how they have a semantic cache controller. And I will basically hit this endpoint. That's what powers the dashboard. And it takes input. It then generates embedding in bytes. So that's a utility function I have here. So that, of course, is a wrapper around generating embedding. So that in turn makes a request to Ollama model that I'm running locally. Ollama is a framework for running various local models. And I'm using a library called Ollama4j to simplify integration. So I'm making a request. I get back the result. I then convert it from double floats to list of floats. I'm sorry, from list of doubles to list of floats, and I return it. Here, I then convert it to a byte array. Again, that's just something that I had to do to integrate with Valkey. And then it gets returned here in bytes. So now I'm going to perform vector similarity search against the index. So that comes from this code. And you can see here that I'm performing a search, but first let me show you how the index is created. So this code, create index, runs on startup when my application process starts. And I'm using a library called Redisson, which gives us our search. It's a Java library. So I specify this index options, and then I specify this field index of HNSW vector. And I create the index with this name. And then I specify these options and this vector. So that's what creates index. But now that it's created, on my HTTP request, I can search it. So here's I create our search query. I specify the fields that I need. I then specify what data I want to return. Again, I want to return actually the input, which I will need, and I want to return the score, which is what I used for similarity threshold. And here you can see that I'm kind of perform the search, and now I'm looping through results. And here's where I'm checking my similarity, my score against my similarity threshold. And if it's greater than, I include the results. Otherwise, I don't. And that's what allows me to control the similarity search. Okay. So now that these results are returned, I check if they're empty. If they're empty, then I save the embedding. And I assume that my top result was the actual input text. But if the results are not empty, I then use the top result, get 0, and I grab the input, which is stored in valkey. Then I check my cache. So I take the input, then I basically use this Redisson library to get bucket, which is just a wrapper around the string. And if cached content is found, I return it. So here I have cache value, and if it's present, I use it. However, if it's not present, this is where I query LLM, which is the expensive inference query. Again, I'm using the Ollama library to make those requests. And then I take this LLM response and I store it in cache for a period of time. And I return it to the client application. Okay. So as I briefly mentioned, Redis-search and valkey-search are slightly different libraries. So Redis-search was actually the very first module that was developed for Redis, like almost 10 years ago. And it was targeting the full text search. And later they added the vector similarity search features. valkey-search started almost 2 years ago when Valkey project was born. And it first targeted vector similarity search, which became a very popular use case. And the recent version of valkey-search actually added a lot of features to be compatible with Redis-search for full text search as well. Now, depending on which library you use, because there are a lot of abstractions built on top of it, such as LangGraph and LangChain, you may have some minor compatibility issues, especially with older versions of valkey-search. But with the newer versions of valkey-search, most libraries should work. But you might see errors, so please test your code. Okay, some references. As I mentioned, I use this framework called Micronaut. I use Java library Redisson. I used Ollama for J, and I'm running Valkey locally. And I'm running both Valkey and Ollama locally. And here's where I also reference this useful article on some of the cool features in valkey-search. Thank you.